I can start. Stream, okay. Right. So can I start? Good. So, yes. First of all, thanks for the invitation. It's a pleasure and an honor to speak to this audience. So I'm Stefano Negro. I work at NYU at the moment as a postdoc, and today I want to speak about the subject of irrelevant deformation. So the title is sort of a pun, the relevance of being irrelevant. And the results that I will present here are based on work with Camilo Florida and Sesen Zamolochikov, which appeared some months ago, and the more recent work with Cordova and Shaposnik, which appeared very recently now. So they are very closely related, these two works. So I will go through them during this talk. So this is a table of content. I will first start with an introduction, and I will, just to set the stage, I will speak about what I mean by deformations, so what are irrelevant deformation, and the picture of the space of theories. And I will introduce the most famous of these irrelevant deformation, which is the TBar, which is spelled either with like this or TBar, sometimes with a math spelling like this, but so they are they have the same meaning. So I will talk about the TBar operator, which is the most famous, the most simply explained type of these irrelevant deformations. I will present its main properties, and then I will give some motivations as to why irrelevant deformations are interesting. So why they are relevant. They are interesting theories to study. And so in order to speak about the most general family of what we refer to as solvable irrelevant deformation, I will move from a framework, from a Lagrangian framework, where the important object is the action and the flow of the action determined by these irrelevant deformations, to the picture of S matrix, and so to the scattering picture. And in particular, this will be fundamental when studying integrable quantity theories and this class of deformation, because this picture allows to make direct contact with the thermodynamic Bethe-Ansatz. So it allows us to compute the finite the ground state finite size energy and the effective central charge and so on. And I will explain a bit how it's done. And then I will show the expected analytical properties of the ground state energy in this class of deformation. So what do we expect to see, and why do we expect to see this kind of properties? I will briefly mention the numerical approach that we used in these works, and then I will present some numerical results and evidence for various kind of models. What is the one that's called 2CDD models, the elliptic Sinch-Gordon models, and finally I will present the curious result that we got with Lucia and with Lucia Cordova and Fidel Shaposnik about what we call them the bosonic minimal model, which is probably not a very good name. Essentially, these are model defined by an S matrix, which is the same as the minimal model deformed by phi 1,3, but with a minus sign in front. So they are somewhat bosonic in that sense. And finally, I will come to conclusions on that. And if anyone has any question at any point, please let me know, because I don't think maybe I can see that in here, but yeah, just stop me and let me know if you have any question. Okay, so the introduction. So I wish to talk about deformation and in the space of theories. And in order to be consistent all through the talk, I will fix the dimension of the space-time dimension that I consider to be 2. So I will consider only theories in 1+1 dimension or 2 dimension, depending on the sign. If I choose to be Euclidean or Minkowskian, usually I will just think of being in Euclidean space. And so let me consider a theory which is close to an RG fixed point. So we are close to a CFT, And the action that describes this theory in general can be expanded as the action of a CFT perturbed by a relevant operator, usually by a set of relevant operators. Here I just put one operator, but I can put more than one. It doesn't change anything. And in general, I also have contribution. If I just choose a random point close to a CFT, I will have contribution coming from irrelevant operators, these are delta J, and I might also have a contribution coming from marginal operator. I simply don't write them because I'm not interested in them, but they might be there. So relevant, I don't need to explain you what relevant and irrelevant mean. It's a statement about the scaling dimension of the operator, and relevant and irrelevant refer to how much they matter when one flows with the RG flow. So what do we know about this theory? Just from the start, we know that whatever is in these square brackets, so CFT deformed by a relevant operator, is a UV complete theory. So it's a theory that is consistent at all scale. We can go deep in the UV and still have a theory which is well-defined, controllable, and that has predictive power. However, when we have irrelevant contribution of this kind, in general, what happens is that the UV completeness is broken. So the theory that is the theory that is written here as it is an effective theory. So it's a theory that is valid until we reach a certain scale, and then we lose control on a theory. Essentially, if we do a perturbative expansion in the alpha I, we see an accumulation of UV divergences. We need an infinite number of contour terms, and the theory is not renormalizable, and we have no predictive power. So that's the standard picture that we learned in courses of QFT. Now we can say something more about this. And in particular, I want to take the perspective of Wilson and Kogut from '74, where the main object in study is the space of quasi-local field theory. So this is a space, and each point of this space is labeled by an action equipped with a UV cutoff, which I denoted by lambda. And the action is quasi-local. What this means is that it is an integral over the space-time of a Lagrangian density, which depend only on the fields and on its derivatives. And in principle, I can allow derivative of any order, but I must restrict to be a finite number of derivatives. So I don't allow infinite number of derivatives. And the quasi-local denotation of this action, it means that I allow a certain non-locality range, but I allow it only for scales that are smaller than a certain scale, which is lambda to the -1. So essentially what happens is that I have each point of this space describe a QFT only up to a certain characteristic length scale. Then after that length scale, I'm not sure that my action actually describes what I want. I'm not sure that I have control on the action once I go past the scale. But up to there, everything works out. And now on this space, the renormalization group acts as a flow. So I specify a certain scale L, which usually is taken to be the logarithm of epsilon. And I define the action of the RG group by identifying a vector, which I denoted by B. It's an element of the tangent space of this space of theories at the point A. So this vector, you can think of the tangent space as the space of fields, or the dual one is the space of coupling. So it gives you the possible direction, the possible element that you can use to deform your action. And then you set up a flow in this way. And the QFT, a QFT, is defined to be the integral curve of this flow here. So in the space of quasi-local field theories, QFTs are not actually points, but they are curves. And each point on the curve describes the same QFT, but at a different scale. So when we move along the flow, we are actually changing the scale. This is the definition of our normalization group. We are changing the scale at which, with which we look at our system. So when we want to integrate this flow equation, we can choose to integrate it in forward time, so going towards large scale properties. And in this case, we don't expect any kind of problem. That's because the theory was describing well the system up to a certain scale. And if we look at larger scale, we don't expect any problem to arise because we already have a good description. However, if we go to smaller scale, so we move towards the UV, in general, we expect a pathology. And for the same reason that I told before, we have a good description up to a certain scale, and we don't know what happens if we go to a smaller scale. We might need to add, usually what happens is that we need to add degrees of freedom to the system, and we don't have any knowledge about them beforehand. So what's the situation is that in general, there exists a value of L, which is L star, such that when we move past, past in the negative direction, that value there, the action that we obtain through the flow escapes from the space. So our trajectory in the space of quasi-local field theory escapes from the space itself. And this defines an intrinsic UV scale, which, for example, in the case of QED is the Landau scale. Now, there exists a subspace of this space of state for which this trajectory have a value of L star, which is infinite. And this is the subspace of UV complete QFT. So theories for which I can remove consistently the cutoff, the space of renormalizable theories. Okay, and here is a pictorial representation of the situation. Usually we start from a CFT here, we can deform with a relevant operator, and then what happens is that we follow the flow and we know that we will end up in another fixed point, which can be either a CFT or an empty theory, also in the case of massive gapped theories. However, if we choose an irrelevant operator, we just follow the flow, and at some point we will just escape from the space at a certain value of L star, which is this one. Now, what I want to emphasize is that there exists a set of irrelevant operators, which in this case here I denoted only the TBar, but there is actually a family of them, depending on the symmetries of the theory, for which the situation is very similar to the irrelevant one. So we follow the flow and we go towards the boundary, but we don't really escape from the space. So this question mark stands to remind us that we don't really know what's happening there. We know that what's happening here is not the usual UV behavior. It's not a Wilson kind of UV behavior. But still, we have full control over what happens here. It's not the same situation as here, where we just escape and we cannot use whatever is the description here. We know that we know how to describe things here, although it's complicated and the interpretation is difficult, but we still have control on the theory.
But L star is not infinite in that case. It's
Sorry?
L star. Oh, I mean,
we have something which plays the role of L star, which is the Hagedorn point, where we find a singularity, a branch point in the ground state energy. There is the entropy that develops a singularity there. So I will mention these things.
You cannot go below this. I mean, up.
Well, you see, the point is that we can, because we have, for example, we have an S matrix which is defined at all scale. So in principle, we can, but what we see is that the ground state energy becomes complex, or the effective central charge become complex. So the problem, it's a problem of interpretation. It's not a problem of control. We know how to compute certain things, even at very high energy, but we don't know exactly what they mean at the moment. We are trying to understand, to give an interpretation. Okay.
Stefano, I just don't understand if this CFT to CFT path, if we perturb by relevant operator, we go to massive regime. No?
Sorry, can you say
this CFT to CFT path?
Yeah,
there is phi delta here.
Yes,
I thought we go to massive regime as usual, but your path ends by CFT.
Yeah, no. Yeah. In general, these, well, the most usual situation is that here we have an empty theory.
Empty, you mean free? Or
Yeah, free. Like when you have
let us take 513 perturbation of CFT. You will
yeah,
get
then you have a gap. You have a gap
not empty.
theory.
You have
You have a gap
that means-
theory and you close.
Okay. And then my question is, Alyosha Zamolodchikov have considered this Eisen and three critical Eisen, and
Yes.
perturbation was look like TT. No?
Yeah, that is actually one of the first first appearance of this operator, where so he was looking at the large long wave limits,
Yes.
and he saw that when you take this relevant deformation and you look at it from the IR, you see that the perturbing operator, so to speak, the operator with which the flow approaches the fixed point is a TBar.
So I would.
So essentially, it's
like TT is CFT, and maybe question.
Yeah, so it's
Why
something
delta
like,
is go to massive theory?
usually
Okay,
yes.
this is your way of representing.
No, but there exists also the situation of massless flow. So there are flows that don't introduce scales, for example, and then you have a flow which connects to CFTs, or you might have a residual.
Can you give us an example?
Huh?
Can you give us example of relevant perturbation and get which end up is
the imaginary the sine Gordon with imaginary mass.
Typically, Slav, you just change the sign of the coupling and you will get some fixed point.
Changes the sign. Okay.
Yeah,
Yes.
You start with kind of negative direction.
Yes.
And the idea of Zamolodchikov was that in a flow like this, when you look at what happens here, when you come into CFT, he found out that TBar was the direction with which the flow approached the IR. So in some way, TBar gives you the first contribution to that. And then you will need probably to add an infinite number of other irrelevant operators to describe the flow correctly. Maybe I will mention something about it later. All right, so what time it is? Yeah, spend a lot of time. Right, so I will quickly introduce the TBar here. So the TBar operator was introduced actually before this this article here, but its properties were mostly studied in the paper in the 16 by Federspin of Alexander Zamolodchikov. And so the TBar operator is essentially the determinant of the energy momentum tensor. In classical theory, everything is good. You can do that without any big problem. But when you consider the quantum version of the theory, then you need to take care of the fact that you are putting two operators in the same space-time point. So you better use the point split procedure, and in order to have control over the singularities that may arise. However, the fact that the components of the TBar operators are conserved currents, so they are, and the important thing here is that they are conserved. It's not really that they are the energy momentum tensor. But the fact that they are conserved implies that the expectation value of this bilinear operator is a constant, and it factorizes. And this you can show using word identities and spectral decomposition. And this is valid actually in any space, not only on space which have infinite direction. That it's a thing that was taught at first, but you can actually show it in general. And most importantly, the singularity that arise in the collision limit are completely under control. And what I mean is that if you study the OPE, these two energy momentum tensor, you see that the first contribution to the OPE is the operator that you're searching for. This is the definition. And then you have contribution of a delta function kind, which are controlled by the trace of the energy momentum tensor, and then further contribution, which have this form. So they have derivatives of local operators. So this means that when you take the 1-point function, the 1-point function of T is essentially the 1-point function of TBar, up to a certain contact term that you can forget about, and just because you can redefine the space of coupling and get rid of the contact term. So I will just forget about this and consider this equality here. So you have full control over your your deforming operator. And this is important because this means that you can actually perform the deformation with this operator without issues, well, unforeseen issues like divergences and things like that. So what you see when you perform the deformation is that the finite size energy on the energy on the cylinder and denotes the state obeys this equation here, which is the Burger's equation. And this equation can be obtained, essentially you obtain it from this factorization using the standard identification on the cylinder, where the expectation values of the components of the energy momentum tensor are given by the energy derivative and the momentum. And so this equation is an equation that appeared in hydrodynamic context and describes the phenomenon of wave breaking. So given a certain profile, what happens is that this profile may break, so might develop with time. In this case, alpha is time in a certain sense, might develop a branch point. And this is what happens if you look at, for example, the ground state, a typical ground state energy. So you have a bulk contribution here and a CFT contribution here. And what this equation does effectively is to perform an affine transformation on this plane. So depending on the sign of alpha, you can either have the situation where the energy at 0 radius goes to a constant, which is an unexpected feature for a quantum field theory. So you would expect that at 0 radius, your theory will have an infinite ground state energy because you have an infinite number of degrees of freedom. But if you perform this deformation, you see that you actually get a constant. And on the other hand, if you have the other sign of alpha, it's a negative sign, you insist on keeping the energy real, a real number, then you won't ever reach the R equals 0 because you have a branch point here. So you have a second branch forming below the first one, given by this. And this can be seen explicitly. So there is a map, well, a procedure which tells you that this equation here is equivalent to this equation here. Here, I just set the momentum to 0 just for simplicity. So think of this as the ground state energy, for example. And so we know the CFT behavior of the ground state energy, which is this one, so close to this value here, we can expand in this way. And here we see explicitly the situation that I described here. So when alpha is bigger than 0, the energy goes to a constant, and which means that the entropy density is finite when the volume is vanishing. On the other hand, if alpha is smaller than 0, there exists a Hagedorn temperature. So there exists a value of the radius for which we have a square root singularity, a square root branch point, and the entropy density diverges at that. And what this means is that when I go and use the entropy density to compute the density of state, I see that the density of state need to have this asymptotic form. For high energy, I have an exponential growth of the density of state. Then Barbone and Rabinovich showed explicitly this for CFTs. But this is general, so this is valid for any TBar form theory. Okay. So just a few words on why TBar and its generalization, this irrelevant, this solvable irrelevant deformation are interested. And I will introduce them at some point, but in a moment. So there are a series of practical reasons. The main one is that these theories allow a high degree of control. As I mentioned, you can describe what happens in the UV. So past this R star, you can find the ground state energy. It's only a matter of interpretation. The problem is the interpretation. It's not the control. These theories are, in a certain sense, are solvable because, like I showed you with the Burger's equation, in this case here, once you know the energy in the undeformed theory, you can extract the energy in the deformed theory. And this is true in a certain sense for this large family that I will introduce in a moment. So they preserve existing symmetries, in particular integrable structures. So if you start with an integrable theory, you will still have an integrable theory. It is universal, at least TBar is universal, because you can define it you can define the deformation with TBar for any starting theory, as long as the theory has an energy momentum tensor. And similarly, this family of generalization, you can define it whenever your theory has higher higher conserved currents. And if in particular you are in an integrable theory, then you have an infinite number of conserved currents, and you can choose to substitute the energy momentum tensor for any of these currents in the definition of the TBar. So you get an infinite number of an infinite family of deforming operator. And one thing that was shown in the article by Smirnov and Zamolodchikov is that this family, this very large family, is in one-to-one correspondence with the possible factorized S matrices that I will mention momentarily. And this means that essentially this family of deformation span the subspace of integrable QFTs in the space of quasi-local theories. So essentially, when we go and study this family of deformation, we are actually studying the whole space of integrable QFTs. And there are some further important motivation. So I only list some of them. So one is the non-Wilsonian UV behavior. So it's an interesting situation where we have a UV behavior, which is not the standard one, but we have control on that. So as I mentioned, the question now is how to interpret the various features, so the Agathon spectrum, the possible non-locality of this theory, and so on. And these features are robust, as I said, we can describe them. So these are sensible extensions of the Wilsonian QFT paradigm. And of course, these features are also seen in string theory and quantum gravity. There are close connections to these deformations and string theory and quantum gravity. So string theory, for example, if you deform the free boson with TBar, you get Nambu-Goto. So this, on a classical level, this is well defined, and this gives you a certain hint about the connection. And you can, another result is that you can recast the TBar deformation as the coupling of your starting theory with a Jakib-Tatel-Bohm gravity sector. And this is how Dubovsky computed the partition function on the torus, for example. So you get a connection also to quantum gravity. So these relations are actually the main reason why so many people were interested in this deformation. That and the fact that you have control over the RG flow, of course. And a cute application is that comes from the fact that irrelevant operator control the subleading correction to critical behavior. And what I mean by this is that think, for example, of having a lattice system and consider the scaling limit of this system. You tune the parameter appropriately, the temperature, say the temperature appropriately, you know that in the continuum, in the critical, when you tune the temperature to the critical temperature, the continuum description will be a CFT, if the system allows a critical point, of course. Now, you can describe the corrections to these scaling limits, and these are controlled by the relevant operators of the CFT. So in the simplest case possible that you can imagine, where you just have one parameter, which is the temperature, then you will have one relevant operator which controls the temperature, which is the operator associated to the energy. And the free energy here will be expanded in this way, and these exponents nu and A and B will be controlled by the properties of this operator here. However, what comes next is controlled by the irrelevant spectrum of your CFT. So having a control over this operator and over the theories formed by them will give you control over the subleading corrections to the scaling limit. And now, for example, just quickly, if you suppose that the TBar is the lowest dimensional irrelevant operator in your theory, then you can fix these two exponents and give a constraint on this coefficient here, of this form here. So this is just an example, but I thought it was nice to mention this. So it's a possible application to condensed matter. All right, so now I will move to the core of the talk. As I mentioned, this large family of irrelevant deformation that you can define are best described in the context of the scattering picture. So the first thing one knows is that the S matrix of TBar deformed theories are known exactly, and the most general formula was given by Sergei, Victor, and Merdad in 17, and it reads like this. So the variation of the S matrix over the S matrix itself. So here we have n incoming and outgoing particles. Momentas are pi and qk, and alpha is the deformation parameter. The variation of S is controlled by this quantity. And so what this quantity means here, the wedge means this quantity here is P0i, P1j minus P1i, P0j. And so, and then you sum over all the momenta incoming and outgoing. And this is important because if you pair it with the fact that in integrable theories, the scattering processes factorize in sequence of two-body processes. So the only S matrix that matter is the two-body S matrix. Then you can write the explicit formula for the S matrix from this using the rapidity parameterization. And here, so I forgot to mention, but in the whole talk, I will just consider gapped theories. So theories which have a lowest mass, which is m. I will not consider massless theories. In massless theories, the S matrix is not really physical. We have something which we can use as an S matrix, but we cannot interpret it as matrix, because in massless theory, we don't have asymptotic states and all this. So I will just forget about massless theories and consider massive ones. So P is parameterized in this way in terms of the rapidity, and the S matrix, the two-body S matrix, is deformed in this way. This is the original one, and you have a phase in front of it. That's everything that the deformation does to the S matrix. It just adds a phase. And this phase is called exponential CDD factor. What exponential CDD factor means is that it's a scalar function which automatically satisfies all the requirements for the S matrix. So unitarity, crossing, analyticity, and macrocausality, which is a statement about the position of the poles, in particular of this S matrix. So this CDD factor appeared in the study, in the Bootstrap program in the 70s and 80s. So the Bootstrap program is essentially applies a series of constraints to the S matrix, and these constraints are the Yang-Baxter equation, which is some equation that's valid in the integrable theories that fixes the matrix structure of your S matrix. And then you have unitarity, crossing, analyticity, and macrocausality. And when you impose all this constraint on your S matrix, you are able to pin down the expression of the S matrix up to a CDD factor. So you will always have this ambiguity when you work in the Bootstrap. And what people did is to choose the minimal solution to the Bootstrap equation that satisfies the physical condition that you want. So the number of particles and so on. So the CDD factor were ambiguity and were just put on a side. What TBar does is to leave your S matrix intact and just add this phase factor here. And the effect of this, as we saw, it's very important because it alters deeply the UV behavior of your theorem. So it's not just something that you can sweep under the rug. You need, if you have this factor, you need to take it in consideration and to understand what it does. In integrable theories, one important thing is that you can actually take this definition of the S matrix, of the deformed S matrix, as a definition for the TBar deformation. And you can show that the action flow, the equation for the action, so the picture, the Lagrangian picture that I presented before, can be recovered using the thermodynamic Bethe-Ansatz or nonlinear integral equation. This was shown in my work with Roberto, Andrea, and Ispan. And okay, well, this phase gives you a gravitational phase shift, which is of this form here. So you can immediately say that for alpha less than 0, you have a healthy theory. Alpha less than 0, I recall it's this situation here. And for alpha less than 0, you have a healthy theory, but probably you have no local observable. This is something that is debatable at the moment. We are not sure about this, but it seems like. While for alpha bigger than 0, you have superluminal propagation, but still you have a well-defined S matrix. So again, these are problematic questions, things that needs to be understood, and at the moment they are not clear, at least to me. Okay, and now once you have the scattering picture, now that we have that, I can finally define this extended irrelevant deformation that I was mentioning. So I will call them CDD deformation. And what they do, like the deformation that I mentioned here, I take this as a definition. I say, I'm studying a theory whose S matrix is defined by this equation here. S0 is the starting S matrix. It can be the free boson, it can be Sinch-Gordon, it can be whatever you want. And I add a CDD factor in front of it. And this CDD factor needs, because of its definition, to be of this form here. So it needs to be composed of a certain exponential term and a rational term. And the exponential term is an extension of the TBar 1. And this S denotes the set of spins of the conserved quantities of your theory. So depending, like Sinch-Gordon, for example, this S is the odd numbers. For other theories, this S can be a subset of the integer. Usually it can also be, in certain cases, contain half integers. It depends on the theory, so it goes case by case. But the important thing is that I require that this exponential factor is an entire function. So the series that is here must converge for all thetas. So you must not have any kind of pole arising because of the asymptotic properties of this sum. That's because all the poles that are contained in this function are inside this rational factor here. And moreover, finally, these poles are restricted. You cannot put poles everywhere. That's because of the macrocausality condition. They are restricted to have imaginary part which is less than 0, mod 2 pi. And the main reason for this is that I am excluding the possibility of having bound states. So when you go and study the S matrix and the analytic properties of the S matrix, you see that poles that lie on the upper sheet, so between 0 and pi, needs to be on the imaginary axis, and they correspond to bound state. They give rise to bound state. So I don't want that, because I want to keep the number of particles in my theory fixed. And if I do that, then I find out that I need to have the imaginary part of these poles to be less between minus pi and 0. And mod 2 pi, of course, because this is is periodic. And the interpretation of these poles are different depending if the real part of theta j is 0 or not. If it's not 0, then these poles are interpreted as resonances. They have a complex mass, and the real part is the mass, and the complex part is the decay. And if they are equal to 0, they are virtual state. These are not a clear interpretation, at least as far as I know. So I will just forget about this and consider only resonances. So essentially what I'm defining here is a deformation of a certain system such that the deformation adds a certain number of resonances to my theory. to the spectrum of my theory. And I want to see what happens when I add these resonances, what happens to the ground state and to the RG.
Excuse me, Stefano.
Yeah.
Can I ask two naive questions to previous slide?
Yeah.
First of all, in Smirnov Zamolodchika, we get this exponential to sinus expression,
Yeah.
right? And you are saying that usual CDD, is this rational? So what is the statement?
Yeah, the statement
You can
here,
claim that always exponential form can be recasted into a rational, or what is the statement?
well, no, the statement can be so in different ways. So one way is to say, okay, CDD factor are scalar function that satisfy a certain set of properties. If I do that, I see that both this rational and this exponential expression satisfy. So in principle, I can say, well, I look only at CDD factor of exponential type, but I do not impose any kind of restriction on the series. Okay, so in principle, this exponential can be a meromorphic function because of the asymptotic properties of this sum, right? So, or I can do the reverse and I say, okay, I only look at rational and I consider also infinite product of rational factors. And you say abstractly, so what's the name? Yeah, whatever. So you can relate the two. So you can see that there is a formula that tells you that an exponential of an infinite sum of sinh can be written in a rational form. But
yeah, I understand what you are saying. My worry is about if I have exponential form, then I have to choose alpha AS in a very special way to get this pole in a clever way in a rational form.
Yes.
And AS stand in the perturbing in the Lagrangian perturbation by higher speeds. So
yes.
each rational guy correspond to a very special combination of the whole set.
Yeah.
I'm worrying about you are clearly saying there is a pole, resonances of complex masses, etc. But this happened only in these specific series.
Yeah.
So if you do not choose correctly, you will not have this resonance. Or what?
Yeah. That's exactly true. So this is one of the let's say interpretation. Well, so if you choose a rational factor without any exponential, you don't have any direct knowledge of what happens to the action, because you need to do what you said. You need to convert this rational factor into exponential, and then you have a certain very specific sum of irrelevant operators that you add to your theory. Yes, that's true.
But you will say us that resonances are very essential of virtual states. Oh, I don't know. Oh, okay, this is my first naive question. Second one, in the left-hand side.
Yes.
Smirnov and Zamolodchikov provided us formula for sine Gordon for Breezer sector. And alpha or M depends on size of the system. Masses are changes under the deformation.
Yeah.
While you are saying Dubovsky, Gorbenko, and Mirboboy provided general answer. Is there any something specific when alpha or M depends on size of the system and energy of ground state? Because you will use this guy in the TBA. If you are saying these are numbers, okay. But these are not numbers, but are dependent.
So this equation here is an infinitesimal equation. So this equation is true.
Yes. But what is the energy of ground state in this equation?
What is
if it is zero, I believe this is a solution. If it is not zero,
the energy of the ground state.
Yes. Density of energy. Yes. In sine Gordon, we have m squared sinus peak psi, something like this.
Well, but here you're considering the system of an infinite in an infinite plane, because you need to define the asymptotic states. So really, there is no size. I mean, the size is given by alpha. Alpha determines the size of.
Okay, maybe this is not important question for you. Okay, this was naive question. Please
no,
continue.
okay, but yeah, probably I didn't understood. We can talk about it later, maybe.
Okay, thank you.
Okay. All right, so okay, so as I was mentioning, we define our theories like this, and we want to see what happens to the ground state. So one way to do that in integrable theories, which is very powerful, is use the thermodynamic Bethe-Ansatz. So the thermodynamic Bethe-Ansatz equation is as an equation, which is this one with star, for a certain quantity, which is called the pseudo energy, that only depends on the S matrix. So it only depends on phi. And from the knowledge of epsilon, once you solve this equation, if you can, then you can compute the ground state energy, A0, via this equation here. This is an extremely general feature of integrable system. And it can also be extended to include situations where, so the idea here is that you use your infinite plane as matrix, so infinite size system, to study the system at finite temperature. You put it on a torus and you see the torus in two different ways, depending on how you put the quantization, with the direction of quantization. And from this, you take then the limit of a very large torus and you say, well, this limit equally well gives me a statistical system in finite temperature or a system in infinite size. And the partition function must agree with that. And then from this statement, you derive this equation and the expression of the energy. But depending on the thermodynamics that you choose on this torus here, you can also have different driving terms. These are called driving terms, these expressions here. So you can have higher cosh, like cosh 3 theta, cosh 6 theta, but depends on the situation. But the usual situation is this one. And now from the knowledge of the ground state energy, you can derive a very important observable, which is called the effective central charge. So this is denoted by C tilde. And this is a quantity that interpolates between the UV and the IR central charges. So when you take the system, size of the system that goes to infinity, you are actually going towards the IR. And since, as I said, I'm considering gap theories, this quantity goes to 0 as R goes to infinity. And you can show it explicitly from this formula here. You just send R to 0 and you see that epsilon needs to have a certain asymptotic, it specifically needs to go as R cosh. And then you substitute this quantity here and you find out that C has this expression. It's controlled by the first Bessel function, Bessel K function. On the other hand, on the other limit, so when R goes to 0, you're going towards the UV. And you know by definition of the energy on the torus and whatever, you know that the expression for C in this limit needs to be of this form here. So it needs to have the central charge of the UV CFT minus 12, the contribution of the primary operator of minimal dimension. So in case of unitary theories, for example, this one says 0. And so you just add the CUV. And then the subleading correction to that will give different combination of C and delta. And so in principle, if you have control over subleading correction, you can distinguish C from delta and delta bar. But if you just have the limit, you are restricted to this expression here. And the R goes to 0 limit is a very tricky limit. It's not evident how to compute. I will mention it later, that there exists a formula to compute this limit here analytically, but just for the moment, just take it as it is. Numerically, if you solve this equation numerically, you can obtain a value for this quantity. Okay, and now when I deform my theory with a CDD factor, I am deforming effectively this phi because I'm deforming S, right? So if the deformation is an exponential CDD factor, then what happens is that I will get an additional term, so this term plus a certain contribution of the CDD factor. And these CDD factors, since they are of kind A sinh S theta, what they do is they deform the driving term. So for example, TBar, what it does effectively is to shift the radius in this way. And this is what happened when I showed you the equation, the solution for the Burger's equation, the functional relation. This is exactly the shift that you have in the radius. So the radius of your system is shifted by the energy of your system in this way. So for exponential CDDs, you have a certain ease because you don't really have a different equation. You have actually you have a different equation if you have higher spin because you have higher contribution. But if you think of considering TBA equation with a generic driving term, that everything that happens is that the driving term gets the parameters of the driving term get shifted. This is all that happens. So in a certain sense, these are easier to deal with. However, when you have a rational CDD, there is no exact result, and you need to rely on numerics in order to understand what happens. Actually, this is not entirely true. You can do some asymptotic analysis, and actually this is pretty important. The realization that I and Sasha had is that if you consider the R goes to infinity, if you think about TBar, the R goes to infinity asymptotic of the ground state energy had two values. So your ground state energy had two values. So the idea was to look at this asymptotic in a general case and to see which are the possible behaviors of the pseudo energies and under which condition you have different asymptotics. And what we saw is that aside from the standard asymptotic, which is the usual one, it's always possible. You always have this possibility. You also have different possibilities. So you can have epsilon vanish at large R. Sorry, these two should be capital R's. They are small r's, but they should be capital. It can either vanish at infinity, but this is only possible if you're considering the TBar case. It can be shown that this is the only possibility. If you have a different kind of CDD contribution, then this is not possible. It's you cannot have this kind of asymptotic. However, there exists a third type of asymptotic. So the pseudo energy can always goes to infinity, but is negative in a certain region of the real axis. Now, if you allow this, then this is a different kind of asymptotic from this one. F is a certain function that I will, that satisfies an equation. I will present it later. And you see that this situation, you can prove it's only possible if the L1 norm of the kernel, so this integral here, is bigger than 1. So, and the important fact, a very important thing here is that this L1 norm measured the difference between the bound state and resonances of your theory. This is another thing that you can prove. And so what this means is that whenever you have a situation in which the spectrum of your system has more resonances than bound states, so actually this, the phi1 is the number of resonances minus the number of bound states. So whenever you have one more resonance than bound states, then your system allows for this asymptotic here. And now, since you have two different asymptotic, you expect that your TBA solution will be at least two valued, because at R goes to infinity needs to have two values. Then at finite value of R, anything can happen. You can have multiple values. In principle, you don't know, but you know that it needs to be at least two valued. And this creates a problem because the usual numerical procedure, which consists in taking a certain initial guess of epsilon and then just iteratively plug in this value until the solution converges. This procedure here is doomed because of the presence of branch points. So when you move with R, when you move with the radius and you approach a branch point, then in principle, your iterative procedure might crash. And this is exactly what we saw. What we did is to take a certain CDD factor, take this TBA and compute the numerically perform this iterative procedure. And once we got to a certain value of R, we saw that the procedure stopped working and the solution just exploded and we couldn't find any solution. So we needed a numerical procedure which was able to handle singular points. So I'm running a bit late, so I will go.
Stefano, could
Yes.
you make a simple comment?
Yeah.
Second situation, you said this is only possible in TBar.
Yeah.
But here we have rational CDD.
Yeah. So
and before that, you said that in TBar, only these driving tones change. Looking for two, how do you say this is TBar situation? I just do not understand terminology. This is only possible in the TBar. TBar, we agreed, is exponential CDD.
Yeah, then if you substitute the exponential inside here, you see that phi becomes phi plus a certain constant times cosh, right?
Mm-hmm.
Then you split the cosh. It's cosh of theta minus theta prime. You split it into cosh theta times cosh theta prime, because the sinh do not contribute because epsilon is symmetric. And then what happens is that the cosh theta prime integrated against log is the energy.
Okay, but then 1 and 3 are CDD, but not TBar case.
Yeah, exactly.
How to understand this?
Yeah, this is how to understand this. So this expression for epsilon, you find it from this shift here.
Yes.
Right? When you send R to 0, E of
yes.
E0 of R is a certain inquiry, so this goes as 1 over R, and then it's fine.
And 1 and 3 cannot be.
And what happens for other CDDs is that if you try to plug this asymptotic in here in general, then you see that phi needs to be divergent. The L1 norm needs to diverge, right? Because you have something that goes to 0 here, but something that goes to infinity here, and you need to compensate. And the only way to compensate is that the norm of phi needs to diverge. Okay?
Can we think naively that TBar do not cover all possible CDD factors?
No, it does not. It does not.
Mm-hmm. Okay.
Yeah, okay, so that was your question. Yes, no, it does not cover all. You need to consider higher spin if you want to have these fractional CDDs. Yeah.
Yes, thank you.
Okay. All right. Then about numerical, I will try to be as quick as possible here because I'm kind of over the time. So the idea here is very simple. Is instead of trying to find solution epsilon of theta and R, I introduce an external auxiliary parameter, which is called pseudo arc length. So and I use these to parameterize my solution. So what I do is instead of finding just epsilon, I search for epsilon and R as a pair of solutions parameterized by this zeta, by this sigma, by sigma here. And what happens is that now I follow the solution curve determined by this, varying sigma by small steps. Instead of varying R by small step, I vary sigma. So I let R be this again should be capital R, sorry about that. I let R be determined by the equations themselves. I don't fix it beforehand. And this gives a leeway and allows the solution curve to be single valued, even if epsilon as a function of R is double valued. And this is why this method works. And why this method can move past the branch point and can handle bifurcations and turning points and so on. And it's a very powerful method that is usually used in bifurcation theory in dynamical systems. Further in our work, we slightly altered this method so that we could accommodate complex solutions. Epsilon, we could allow epsilon to be a complex numbers. And so we could actually follow the TVA solution in the whole R bigger than 0 region. So both when the solution is real and has 2 branches, as I will show, and below R star where the solution is complex. And we could extract the limit of this effective central charge. So this is the typical situation. And this is actually universal. So whenever phi this norm of phi is bigger than 1, we always saw the same qualitative situation. We always saw a standard asymptotic, which is this blue one, a linear asymptotic, which is the other one, the 3 that I mentioned before. And in between, we saw this branch point, this square root behavior of this kind. The qualitative picture is always the same. It is irrespective of what kind of deformation we are considering. This is always the case as long as this is valid, as long as we have more resonances than bound states in the spectrum. Okay, so I will just breeze through the numerical result and then go to the conclusion. The models that we considered are in the article with Sash, with Zamolodchikov and Camilo, Fleury, and Lenses, we considered these kind of models. So models that have 2 resonances with 2 poles, and we studied the various ranges of these 2 poles. And what I consider the most interesting is when I send U2 to I infinity with a certain shift, then what happened to this matrix is that I get the bosonic version of the 1 resonance as matrices. What I mean by this is that if I take U1 to be minus pi 0, this is Sinch-Gordon as matrix, but with a minus sign in front of it. And what we saw is that if we consider these kind of theories, like this bosonic counterpart of Sinch-Gordon or bosonic counterpart of staircase model, which is when U1 has these values here, both the theories have the branch point that I showed before, even though they have apparently a single resonance. So this minus sign that appears in front of this matrix effectively makes the theory 2 resonance model. And you can see that explicitly. So if you consider there exists a map between the TBA and the bosonic sign and fermionic sign, and this map essentially amounts to shifting this matrix by a delta function. And this delta function gives a +1 when you consider the norm of your kernel. So this effectively, this minus in front of this matrix acts as if it was a resonance. And the effect is that you get the usual qualitative behavior. So this is valid for any range of parameters considered. You get a standard branch with usual asymptotic, the R-cosh asymptotic, a second branch which has this asymptotic, again, R should be capital, and F satisfies this linear equation here with a certain value of B bigger than 0. So you integrate only on a subset of the real line. And from this information, and also from the subleading contribution to epsilon, you see that the energy has this behavior here. So it has a linear contribution. This on the second branch, on this red branch here. The energy behaves linearly in this way and has 1 over R to the cube contribution. The 1 over R contribution that you expect to have, it cancels exactly, as you can show. And another important thing is that R star is not a function of theta. So you get a branch point only in the R dependence of your quantities. So it's somehow global in theta. And this was a thing that confuses us a lot at first because we thought it needed to depend on theta. And also we saw some numerical suggestion to that, but actually this is not the case. In every case we studied, this is always the situation. Always, you actually get a Poisson series, so you get a series in the square root of R minus F star, which in principle you can use to do some computation, although it's very complicated. And so this is some picture. So here you see explicitly this is the pseudo energy with respect to theta, and the red values are above the branch point and the blue ones below. And you see that when you go past the branch point, you really get this negative region where epsilon is negative in a certain subset of the real line. And this is an example of the Y function. I just put it because I think it looked nice. In the case, in the 2-CDD case, when the parameters have this structure here, when we send gamma to pi over 2, then the equation becomes singular, and you can actually reduce it to a finite difference equation, which we call the narrow resonance equation. which is reminiscent of the Y system, but it's different because it has this arc here, so it's kind of different. And we studied this, and we showed that it actually corresponds to the limit. And this is interesting per se. We didn't work that much on that, but we are planning to explore this equation more thoroughly. Okay, so the other models that we studied this with Cordova and Shaposnik is this infinite resonances matrix. So when you take essentially Sinch coordinates matrix and you substitute the Sinch for elliptic sign with a certain modulus L. So this is a matrix which has an infinite number of zeros, well, two lines of zeros, two infinite lines of zeros, or two infinite lines of poles in this way. So it has infinite resonances. And what we saw is this. So this is the pictures, the kind of pictures that we get. They are essentially the same as we saw before, only here we were able to go to in the complex domain, so below R star. So we see the standard behavior at a large R that then melts with the non-standard one, which is given by this, with a square root branch point. And below that, everything becomes complex. We have complex values for the effective central charge. And in particular, for this model, what we saw is that when we go to R goes to 0, everything goes to 0. So the effective central charge, the limit goes to 0. The limit of R goes to 0, effective central charge goes to 0, which is curious. And you can actually show it. Well, okay, this is the trick that I told you before to compute the limit of the central charge. You can manipulate your TBA equation to find this relation here where y0 satisfies this equation. And if you use this, you can actually see why in the elliptic Sinch coordinate model you find 0 for the effective central charge, because as this quantity grows and goes to infinity, the solution condenses on this circle here. And the correct solution are the one that minimize the absolute values with 0. So we get 0 from that. Okay, and finally, the last thing that I want to mention is if you consider models with bound state. So for example, 513 deformation of non-unitary minimal models, this kind here, and deform them with a CDD factor. In this case, we chose the simplest one, so this -1 that I mentioned before. These are the S matrices, the undeformed S matrices. What we see is that, as we expect, since we have more bound state than resonances in this case, our model is UV complete. So we can go to the UV without any kind of problem. There is no discontinuity, no branch point, and so on. And we saw it explicitly. So we were able to compute the effective central charge CA for, this is the top one is the sum of the single particle contribution. And what we saw is that C, apparently the UV central charge is not rational. So these are the values that we found. We are not sure, of course, that it's not rational because this is numerics, but it appears not to be so. Okay. So to finish, we explored the vast space of generalized TBar deformation, and this scattering perspective make contacts also with the S matrix bootstrap. I didn't mention it, but this is quite relevant in the context of S matrix bootstrap, because with this technique, we can actually explore the whole space of consistent and factorizable S matrix. And it appears that the majority of these S matrices is not derivable from a local QFT. So if you just choose a random factorizable S matrix, chances are that this S matrix is not derivable from a local QFT because it has this Agathon transition and this phenomenon. However, we found a condition on the spectrum for the presence of a standard UV, and this condition is not related to anything that makes the theory integrable. It's a statement about the spectrum of the theory. So it is possible that this statement generalizes to non-integrable theories, and it will be interesting to try to understand this point. we introduced this new numerical technique, and we discovered, which I find interesting, a new family of integrable S matrices with a well-defined UV behavior. The weird thing is that these models, the last one that I presented, they never appeared in the literature, so no one really thought about studying the S matrices that you obtain from these deformed minimal models with a minus sign in front of that, which I find interesting. And so for outlooks, it will be one intriguing thing is to, since we can access this complex domain where the pseudo energy and the effective central charge are complex, it is intriguing to think that there exist complex CFTs that control the UV behavior of these theories. And so it will be interesting to go and look at the subleading behaviors and excited state TBA to understand the scaling dimension of the operators involved in this CFT and try to understand what kind of CFTs we are dealing, if they really are complex CFTs and so on. This is a sort of a not well studied subject, so, but I think it's an interesting perspective that might be worth following. Another thing to do is to consider a general CDD model with bound state, like the minimal model that I showed before. And we expect that there might be a lot of UV complete systems that were never found before. And in particular, what the next thing to do, I think the most direct generalization is to consider CDD deformed 513 unitary minimal models. So like the one that I showed before, but unitary, from the unitary series. And keep investigating the TBA for R less than R star. One thing that Sasha noticed is that complex solutions usually signal an instability of the ground state, and what's not clear is against what kind of decay. So there should be some kind of nucleation process, maybe. We are not really sure about what happened, if the ground state is stable, how is it stable, if it's unstable, what causes the instability, and so on. So these are like deep question of interpretation of the theory, these theories in the UV, as I mentioned before. This is what we need to understand. And of course, there are a lot of other things to do, but I just concentrate on these ones at the moment. So thank you very much for your attention, and sorry for going long. I'm here if you have any questions.
No, it's fine. We're typically going long, so it's fine.
Yeah, okay, good. Yeah.
Okay, questions?
Excuse me, what happens to local local operators after TBar deformations?
Yes, so there is this belief, and I think that Cardi quite successfully showed in his next to last article, I think, that operators, what happens when you deform your theory with TBar is that effectively your operators get dressed by some kind of gravitational line. So the idea is that TBar is composed of conserved currents, right? So you can use the conservation current to make the operator to solve explicitly these and make this operator into a semi-local operator. I don't know if you ever saw this procedure, but essentially,
in what sense?
So what happens is that you deform your action with the TBar, right? And TBar is an integral over the space. The deformation is an integral over the space of this TBar operator, right?
Yes.
Now, every expectation value that you compute will be corrected by integrals over the space of the expectation value with the TBar inserted. Okay? So the insertion of TBar will deform your expectation values. Now, since the TBar is composed of conserved currents, you can write the integral over the space as an integral over the boundaries of your space of a certain semi-local operator. So an operator with a tail that goes to infinity. And these tails, what it does is effectively wraps up all the insertion that you have in your space-time. I know it's maybe it's difficult. I don't have a blackboard to show you, but the picture is really that. So if you consider, like, suppose you have a certain set of insertion, like let's say 10 insertion in your space-time, and they are
Okay.
effectively singularities, so points that you remove from your space-time. When you deform with TBar, the TBar goes and wraps each one of these singularity with a certain line, which is essentially is a Wilson line, and connects them with this line. So you can look at the net effect as each one of these insertions has a line that goes to infinity, a Wilson line that connects them to infinity. And so when they move around, you have non-trivial topological situation where these lines wraps around each other. This is
But in the initial theory also has some quasi-local operators. We can define quasi-local operators in any local quantum field theory.
yes.
What new? What is changed in the non-local theory?
Well, in the TT, no, the fact, yes, okay, the point is that each one of the operator that you insert in your theory will have this non-locality. All of them. So in
all of them are not non-local to each other, but quasi-local.
Yeah, exactly. So, exactly. It's that. So if you consider them isolatedly, well, in isolation, they are local, but they are non-local to each other because of these tails. So
when you see this phenomena in Nabu-Gotek theory, in bosons.
I didn't study it, so no. So the short answer is I didn't see it, but I believe that you can see it explicitly.
Probably if we start with some non-local guy, then by tracing it, we can get some local, no?
Okay, well, no, this is an interesting thing. This is related to one thing that I noticed, that if you consider like one random CDD deformation, right, you have a universal form of the energy, and now you can try to act with TBar, but with the wrong sign, so as to turn back this behavior to the usual UV1. So instead of having like this branch point, you try to cancel the branch point with the TBar, and you can actually do that and find a theory which has a UV, a divergent UV behavior for the ground state energy, but the divergence is not 1/r, it's of a different kind. And this is probably related to what you were mentioning, like trying to use TBar to cancel the non-locality of a certain operator, like to offset this non-locality up to the point where you don't see it. That's an interesting perspective. Yeah.
Sorry, I have one question.
Yeah.
Sorry if it's not from the agenda, but you were talking about a Cindy-Gordon model, which has non-relativistic limit, of which is non-linear Schrödinger model.
Yeah.
And there's a problem that if we turn on the deformation, we just lose this relation. And so I'm wondering, is there some general sense of what is getting wrong, probably?
So I didn't get what you lose. You mentioned when you turn on the deformation, you lose what?
I mean, if you have, so if we deform the Cindy-Gordon model and
Yes.
and take nonlinear, non-relativistic limit, so
yes,
we don't get deformation of nonlinear Schrödinger model. So okay, you should.
Okay, so what I never looked at it, so I'm not sure I'm the right person to answer to this question, but I know that there was a work by Tateo, a recent work, which dealt with the nonlinear Schrodinger equation, and probably also, I think there were also other works before that. I can try to search them. But if you search Roberto Tateo on Inspire, say the last or next to last work was on the non-relativistic TBar, the deformation for non-relativistic model.
Okay.
Yeah. So.
Yeah, Stefan, I have a question.
Yes.
I probably didn't get it quite. I'm not sure I get it. I got it. So the condition, you formulated some condition for actually having your UV complete theory.
Yes.
So can you just repeat it and explain? Is it like it's you derived it from like physical grounds or just the property of equation?
No. So okay. The condition is this. The condition that so it's an experimental evidence. This condition here.
Yeah.
Now, this is an experimental evidence in system that have just one particle, so no bound state. So of course, whenever you have at least one resonance, you see something like that. This is sort of partially, let's say, encompassing all the models. And that was one of the reasons why we went to study these kind of models with bound states, in order to see if it was actually true that when you have more bound state than resonances, you had a complete UV. And this is what we saw. And then on top of that, there is something that I'm trying to do at the moment. So I'm looking, I'm trying to find a mathematical expression for this condition between bound state and resonances, because I do believe that this is true. I never saw any.
So the condition is that number of bound state is less than the number of resonances?
No, it's bigger. It's bigger.
It's bigger.
Yes.
And
as long as you, all the models that I looked at, as long as you have that condition granted, you have a well-defined UV.
yeah,
well,
but
standard UV.
Is there any physical intuition why this
exactly? At the moment, well, no. The one physical intuition that I have is the fact that so if you this situation, the problem arises at high energy, right? So when you go at very high energy and you look at the poles in your complex theta plane, you essentially look, all of them look squashed on the real line, right? If they are in the lower half plane, in the upper half plane, they all look squashed on the real line and on the imaginary axis, because you look at them from very far. So what I interpret that to mean is that it seems like when you are at very high energy, that both resonances and bound state contribute to your spectrum. But the point is that while bound state, you close the bootstrap on bound state. So once you have one bound state and you need to add another one, and then you close the bootstrap, these are the only two bound states that you will see ever. You don't have any other particle that forms. For the resonances, you didn't do that. So it might well happen that once you have one single resonance, then this resonance combines with itself to create another resonance, and then this contributes with another resonance, and then you have a proliferation of states that, when you look at them from very far, they look like proper particles in your system, and so they contribute to your density of state. This is very hand wavy and very not precise at all, but it's somehow the idea that I have of the situation is that.
And how what will break in the opposite situation, like if you have less bound states, so that then kind of create some complex mass, or some, the state. No, sorry, I don't. So in the opposite case, when you have fewer number
In
of,
the opposite case, I think it's probably related somehow to the fact that you have less particles to start with, so you have less possible particles that come out from that. I don't know. Yeah, it's, as I told you, it's very imprecise as a.
I mean, if you allow yourself to consider everything complex, you're not like
Yes.
afraid of complex numbers, then
Yeah.
so okay, I'll probably have to think. I'm just I mean, from the point of view of complex like on analysis, it shouldn't be. I mean, in all cases you have a solution. They just they have like different analytic properties, and
Yes.
probably means some kind of accumulation of poles coming from out of physical strips, something like that, or what? Then you iterate in this equation, you have like more and more poles in the integrand, something like that.
No, see, that's not okay. There is not a situation of accumulation of poles, but you're talking about the TBA in this case. Yeah, no, in the TBA there is no accumulation of poles happening. It's really, I mean, if you look at it look at the TBar, for example, and look at the situation where alpha is very, very, very small. Then you're very close to the starting theory where you have this discontinuity at R equals 0. Now, what alpha does is it moves the singularity slightly to the right. And at the same time, it curves a bit the vertical axis, so that what you effectively see is a branch point. This singularity, this 1/r type singularity, moves and becomes a square root type singularity. So it's not an accumulation of divergences that you see there. It's really like the moving of something that should be at R equals 0, and now it's no more at R equals 0.
Also, probably a related question. You mentioned CDD deformation of unitary models.
Yeah.
Just to confirm that I understand correctly. So you're saying that if I have like a lot of like, I don't know, the Potts model, for example, then it is safe to deform it by one CDD factor, and you will get the UV complete theory.
I would guess so. Yes, exactly.
So if you so I mean, the more bound states you have, the more factors you can add.
Yes.
And what would be the interpretation of it? So if it's UV complete theory, so you would expect some Lagrangian.
Yeah.
Some kind of
exactly.
So I also didn't get the UV central charge. It changes, right?
Yeah, the central charge changes. So here you don't have the UV. Well, in the UV you would have a rational central charge if you didn't deform it. In this case, you don't. Well, apparently, I mean, I don't know. Maybe these are rational numbers, but very complicated ones. But
which ones?
These ones that are written here. They are the UV central charge.
You can always approximate by rational.
Yeah, no, exactly. That's what I'm saying. Maybe they are like super complex rational number, but I cannot tell. But they, of course, they are not the central charge that you see if you don't have this.
So sorry, n here is what is your n
is the index for the minimal model. So n equal 2, for example, it's Lee-Yang. This one is the Lee-Yang matrix with the minus.
No, not Lee-Yang. What is the central charge? N equal 1 is Lee-Yang. 2, 5.
N equal 1
is Lee-Yang.
Oh yeah, you're right. 5. I'm sorry. Because I put 3 here. Okay, yeah, then I didn't write it down, but for n equal 1, this C tilde is 0.5. So it's the only rational one that we see.
0.5.
Yes.
So instead of negative, it becomes positive and everything.
No, That's a counterpart.
Well,
not of, this is
It's not the
2, 3.
central charge. Yeah, it's,
This if effective is positive.
yeah, this is effective and it's positive. It's not the central charge. It's,
Yes.
it
Yes.
has
Yeah. Sorry.
contribution from, yeah.
Mhm.
This is another thing that needs still to be done, like to go to subleading correction, for example, and look at the subleading contribution to distinguish between central charge and the scaling
so-
dimension.
Subleading contains scaling dimension, which can
Yes, because
which can be
the
negative,
formula is well,
yeah, right.
is this one. So in principle, you have scaling dimensions. And
Mhm.
you need to decouple these, but you need to look at the subleading contribution in order to do that. So this is one thing that we are doing now.
Mhm.
Stefano,
Yeah.
concerning this formula, in Li Yang, we are saying the residue in the pole of two particle number one is negative, that this is reflection of non-unitarity of Li Yang. But now you multiply to -1 and residue become positive.
Yeah.
So the theory is good, or I don't know.
Yeah. Well, okay. Yeah. So this was done very quickly and was an observation that we found nice, and we just fit it inside. So we're still working on this thing. But yes, this is what one of the things that we noticed is that, I mean, in principle, this seems to be unitary.
But could you clear
Yeah,
up?
you see, there is a problem here of interpretation, because if this was unitary and minimal, then these are classified, and it's weird because I don't see the classification here. So either the S matrix is unitary, but this doesn't mean that the CFT that you get at is unitary, which might also be the case. Probably it's what happened.
Also, one of my worries about this phi equal -1. You remember this 20 years ago, Moussard and Simon paper, they claimed bosonic type matrix like this -1 times fermionic.
Yes.
Characterized by the unstable ground state, blah, blah, blah. And we do not know any model which have bosonic S matrix.
Yes.
And now we are saying everything will be okay and central charge this. So no problem with stability of ground state?
No, here, no. You just have one ground state. You don't have any. Yeah, also, I mean, the statement by Simon and Mussardo about the stability of ground state is kind of not supported. I mean, I'm not saying they are wrong, but I'm not saying they are right. Because what we see in the bosonic model, where you have these two branches, we see two branches, but it looks like the standard branch is stable against the decay, which is this thing that I mentioned before. So we don't really understand what's going on here. If there is I mean, one would expect an instability. You have a tachyonic state, so you would expect an instability of the ground state. This is the standard picture.
But even in this case, you don't know the Lagrangian, right?
No,
You
no.
know.
Now, this is related to what you said before. So we have like a rational factor. So we don't know exactly what is deforming the model.
So you just work in terms of S matrix.
Yeah, exactly.
Don't
So
worry about Lagrangian.
No, this is a pure bootstrap perspective where we just worry about the spectrum and the S matrix and don't worry about the action. They might have an action, they might not. We don't know.
And maybe one more stupid question. In usual beta ansatz, we have nice logarithm identities which reproduce all central charges. Here, these results only numerical.
We confirm them with these, both in the real and complex. So we have the logarithm trick. We used it.
You used it, and still results only numeric.
No, in the sense that the C infinity. So, for example, this fact that C infinity for the elliptic Sinch-Gordon goes to 0, this was confirmed. We confirmed it by the logarithm trick, and also we did computation with the logarithm trick for the bosonic Sinch-Gordon. So the Sinch-Gordon S matrix with a minus in front of it. we found agreement with numerics using these expressions. So this expression seems to be valid also when the solution is complex. This was one of the questions, whether it works or not. It seems to work, and we verified all the numbers, also these ones, using the dilogarithm tweak. So yeah, they are numerics because, I mean, I don't know the exact values of dilogarithm over a certain numbers. For this reason, I say they are non-rational, because I'm not sure if these things are rational. But yeah.
Other questions?
Or maybe I have one more.
Okay.
When you have shown us elliptic S matrix, we know S matrices of that form in Forrester-Baxter lattice models. But now what you are saying, this is field theory?
Yes, I'm saying that, as I said before, if you look at it from a bootstrap perspective, what I'm stating is that I'm studying a model that has an infinite number of resonances and no bound state. And
I understand the structure of the S matrix and the
and so I take this and I just say, okay, suppose that I have a field theory that has this S matrix, and then I don't ask anything
but
else.
how can you explain? We know lattice model, we have that S matrix.
Wait, this exact S matrix?
Yeah, I think so.
Okay.
Misha, is it not so? This is just sinuses to elliptic sinuses.
Yeah.
It's Forrester-Baxter S matrix, but this is, or maybe, okay, let me ask in a different way.
Okay.
Let us take sine board and put instead of S matrix, elliptic S matrix, Baxter's S matrix.
Okay.
So you again claim this will be some kind of field theory? I'm just wondering that elliptic S matrix appears as matrix in some quantum field theory.
There is a spectrum beside this matrix.
Yes. And what? What is dispersion relation
so,
in this QFT? M cosine, M sine?
Yes.
Yeah.
Yes. But S matrix is double periodic and energy and momentum is single periodic. Is it not strange?
It's strange.
Yeah, it is strange. I agree.
While only on the lattice we have both of them. Energy and momentum are double periodic, and that S matrix appear.
Okay, so really theta is not related to the momentum by the Gaussian sinch. That's what you're saying.
No. How to say? I'm saying that we definitely know models with that elliptic S matrix. We can write down form factors, etc., etc.
Okay.
But we only think these are off-critical lattice models.
Okay.
You are saying you have QFT.
Okay, I understand.
This is worrying. I mean, I worry very much.
Okay, no, I don't have an answer for that, but I understand your point. So our perspective was simply to take these as an S matrix without asking too many questions, and then but I understand the problem now.
Yes,
because you see the starting idea was to study S matrices in general with infinite resonances, because they appear in the S matrix bootstrap, like the ON Young-Baxter model.
Yes.
And so this was sort of a toy model. We found it in an article by Musardo and Penati. I don't remember.
I remember that paper, but I thought he was writing about elliptic lattice model.
No.
Okay.
You know, he was actually not even asking the question, because he was simply saying, yes, this is an S matrix. Let's study the form factor.
Let us write down form factor. Instead of integral, you will get sums, etc., etc.
Yeah, exactly. And that was it. That was his whole point.
But the question is, what about dispersion relations?
I don't know. Yeah. Okay. This is a good question. I will look into it.
Yes. Okay. Thank you.
Yeah.
Okay, if no more questions, let's thank Stefano. Thanks a lot for good talk.
Thank you very much. Very good
Yeah,
talk.
very interesting.
Thank you very much.
Thanks to you. Thank you so much.
Stefan, I'll put you in the list so in case you might join us. In that case, we'll switch to
Yeah.
English.
Sure. So you put me on the mailing list?
Yes, yeah.
Okay, good. Great.
Uh,
Yeah, that's interesting. I will try to join. I can